This will be our last lecture in representations of supersymmetry. In this lecture, we look at various examples. But first, let me just remind you of the general structure that we uncovered last time. Schematically, working with massless representations. With massive representations, things were very similar, except SOD minus 2 went to SOD minus 1. Schematically, we had Q plus was 2p plus, Q minus was equal to 0, and therefore, setting all central charges to 0, Q minus Q plus was 0, and those could just be dropped. Right? So we were dealing with only the Q pluses. And the Q pluses, so the full algebra that we had to represent in this little group kind of way was the algebra of Q pluses, the algebra of SOD minus 2, and that was it. Now the problem was that SOD minus 2 didn't commute with Q plus. So we invented a fictional SOD minus 2, which we called N, I think, that by definition commuted with Q plus. And then we constructed the actual SOD minus 2, the SOD minus 2 that acts on everything physical, as N plus the SOD minus 2 constructed out of the Qs, out of the Clifford algebra of the Qs. Okay, you remember that, right? Any questions or comments about that? Okay, so we constructed, schematically we had N with Q plus is equal to 0. And then we constructed this sigma A alpha beta Q alpha Q beta Q alpha Q beta. Raising, lowering is always done with C, with the matrix C. Up and down indices, if they're not in the position you expect, you always raise or lower with C or C inverse. Okay. We had this guy, which I don't know, we call something else. Theta, let's call it. And then we had that N plus theta was equal to M, where M was the physical SOD minus 2. And the great thing about this was that M rotated Q plus like it should, because N did nothing to it, but theta rotated Q plus like it should. So now M has the right commutation relations with everything. And then we understood that that to get the final quantum numbers of all states in the representation under supersymmetry, to get the final quantum numbers of all states, what we needed to do was to take the representation content coming out of this the states of obtained by quantizing Clifford algebra, obtained by the representation of this Clifford algebra for Q, and tensor it with any representation of SOD minus 2 times R symmetry that you choose. That's in your hands. And the Klebsch-Gorton of these two give you the full state content. You remember this general procedure. Okay, so in today's class, we'll just work this out in a few cases, just to get sort of familiar. So let me start, for instance, in the case, we'll come back to low dimension in a bit, but let me start first with some high dimension. Let's start with D equals 10. Okay, so suppose D is 10. Now remember, supersymmetries in D equals 10 are characterized by two integers: number of chiral spinors, number of antichiral spinors. Let's take the simplest case. Let's say it's one chiral supersymmetry and no antichiral supersymmetry. All good? Okay, so suppose we have n plus equals 1, n minus equals 0. Then in this whole procedure, all our supercharges are chiral. Remember, Q plus is the part of the chiral spinor that had a plus charge under one of the two plane rotations, 0 and whatever. Okay? So now we want to look at the commutation relations only of the Q pluses. But if you have a chiral spinor of SO10 and the charge of the top guy is plus, then that is the same as a chiral spinner of SO8. Is this clear? It's important you can at least roughly think about spinors. So remember, components of spinors are characterized by their charges, and the charge under any two-plane generator is plus minus half. That's what a spinor is. Okay? Now, it's chiral if the number of pluses is even. Sorry, if the number of minuses is even. Okay? Here what we're saying is that one of these is plus half. Okay? The whole thing was chiral. Clearly it's a spinor under SO8 because this guy is frozen, these guys can keep fluctuating. So it's a spinor under SO8. That's obvious? Okay? So if you fix the charge of a chiral spinor in one of the two planes, what you're left with is a spinor under SOD minus 2. That's clear? Okay? What kind of spinor? Well, these charges fluctuate, but the total number of minuses is even because this guy was plus. And therefore it's a chiral spinor of SO8. Is this clear? We could argue it more formally, but actually this is the way you think about it. It's better to think this way than more formally. You can sort of see it. Okay? So each of these guys, these Q pluses here, will be an SO8 chiral spinor. Is this clear? Okay. So the charges are SO8 chiral spinor. Now the commutation relations between these things, on the right hand side you have something that is SO8 invariant. You get some C matrix or something like that. If you had both lower, if you had one lower, one upper, you get a delta matrix. It's SO8 invariant. Right? The commutation relations are SO8 invariant because this is the part of the rotations that leaves the momentum unchanged. The right hand side had a momentum, but that momentum is invariant under SO8. Would not be invariant under the whole SO10, but it's invariant under SO8. That's the whole point of this little group business. Okay? So what you get on the right hand side is some index structure that is SO8 invariant. It will essentially be the C matrix of SO8. But we can figure out everything we need about it by hand, without looking at detailed structures as follows. Because we've got the right hand side is SO8 invariant, it's invariant under each of the 4 two-plane rotations. And therefore, charges have to be conserved in this commutation relation. So you can only have a non-trivial commutator between something that has some charges and the opposite charges. Clear? So in particular, what we have to do is to break up these Qs. If we want to make the state space on which this Q acts, we have to break up these Qs into creation and annihilation operators. Okay? How do we do that? Well, one way is just to choose one of the two planes of SO8. Let me choose the 4th two plane. So SO8 spinors are now like this. With the chiral, so even number of minuses. Okay? And let's just choose this guy plus and call it creation. And this guy minus. And call it annihilation. Just for fun. This is our choice. Okay? So now what we will have is a state that is annihilated by all the annihilation operators, and then we get the full state space by acting with the various creation operators. So the creation operators themselves are SO8, now SO6, an SO6 chiral spinor. Is this clear? Whereas the annihilation operators themselves would be an SO6 antichiral spinor. Okay? Great. So now I want to create the state space that we get. What I'm doing is the analog of creating the fact that when we do Clifford algebra with vector valued operators, the state space is just spinors. I'm now doing Clifford algebra with spinor valued operators. I want to know what the state space is. It's clear it's going to be in general a bigger state space, because at least at high enough dimension, the number of spinors is much larger than the number of vectors, because one grows exponentially, the other grows linearly. In general, at high enough dimension, it will be a bigger state space, right? So now we want to understand what the state space is in detail. Okay, great. So let me start with a vacuum, and this vacuum has a certain U1 charge. Okay, so we have SO6 and we've got this U1 or SO2 here. Please.
You were saying that we are trying to find the representation of SU2 cross SU2 cross SU2 cross.
Why SU2? Sorry?
Because we are now in the spinorial representation.
So why SU2?
Because each plane is like SU2.
Each plane is like SO2.
Sorry.
Okay? But I'm just using these plane charges as labels. In the end, what I want to do is to find the representation under SO8 of this thing. Okay? It will be convenient for me because, the break, when you divide into creation and annihilation operators, you cannot preserve all of SO8 in that division. Okay? So I will write down representations of SO6 and then eventually combine them into full SO8 representations. Is this clear? Okay? These are just labels for charges. They're labels for a full representation of SO8. Once we go to the creation operators, a full representation of SO6. At least SO6 we will keep around in the game. This is one way of functioning, by the way. Strategy has some other way of, I'll briefly tell you. These are all group theory tricks. We'll play them for 5-10 minutes and then move on. Okay.
And in the case where, let's say, first spinor is, all the others are fixed when, but the first two are taken plus and minus, will that be just some another basis?
Exactly. We will see in the end, the question is equivalent to asking, in the end will you get answers that are SO8 invariant? We singled out one plane, that broke SO8. In the end, if we can group the whole answer into SO8 representations, then we will see that.
So in that case, there will be 4 options.
Yeah. And even
like there will be 4.
Yeah, and even 4 is an undercount because you could have rotated your axes.
Oh, yeah.
There's an infinite number of options. All of it will give you the same answer. You see, we're quantizing with SO8 invariant commutation relations. So the state will be SO8 invariant unless you make a mistake. Mean some representation of SO8. It's just a method of getting it that is breaking. It's like choosing a basis which breaks some symmetry. I will show you, in fact, after this, since we've started this, I'll finish. But I'll show you how you could think of the same way for Clifford algebra, for ordinary Clifford algebra. Let's come back to that for a moment. Okay, fine. So let's take this vacuum, the vacuum that is annihilated by all the annihilation operators. Now, this vacuum is going to have a certain under SO6, it's going to be an invariant, but it's going to carry some SO2 charge. So this was the SO6. And then in addition, there's an SO2 charge that acts on this special guy. Now, let's look at what we're going to get. You see, what is the total number of SO6 chiral spinors? SO6 chiral spinors. 21. No. Come. Number of spinors is always some power of 2. 8, almost. 4. 6. Yes. So you can do some general thing, but you can also look at it. There's plus minus, and there's one constraint. It would have been 8, but it's 4. Right? Okay, so total number of SO8 chiral spinors is 4. And we're going to get states by taking this vacuum and acting with 1 of them, 2 of them, 3 of them, or 4 of them. Okay? Clearly, the SO2 charges will go from A plus half, A plus 1, A plus 3 halves, A plus 2. Because each of these have creation operators have charge plus half under SO2. Now, if we want to get things that to combine up into a full representation of SO8, we will want this to be symmetrical. Plus and minus here will be symmetrical. Okay? And therefore, we will choose this vacuum here to be 0 under SO6, meaning invariant under SO6, but to have charge minus 1 under SO2. That choice is forced on us to get pluses and minuses behaving symmetrically, to get CPT invariant combination. Make any other choice, the answers will not combine up into a representation of SO8. SO6 will be fine, but SO8 won't work. We have to make a guess. Okay, we made that guess. Okay, now let's take one SO8 chiral spinner and act on this vacuum. How many states do we get? Just one of these acting on the vacuum. Well, 4. The number of creation operators is 4. The creation operators are SO8 chiral spinners. Any of them can act on the vacuum. Each of them acting on a vacuum will give us a state. Is this clear?
What is the statement about this vacuum? If you have annihilation operator is 0,
it's 0.
minus 1 is 0.
It's 0 by definition.
And class of increases it by class of.
What? The creation operator gives us whatever it gives, but it increases its SO2 charge by plus half.
Plus.
Okay? It's clear that we will get 4 states at level 1 by acting the creation operators once, because there are 4 creation operators. That is clear? Okay? What representation of SO6 will this state transform in? Very good. What? Louder? Chiral spinner. Because the vacuum was invariant under SO8, and you acted on it with a chiral spinner. So it will transform like a chiral spinner. So let's call this 4C. 4C means the chiral spinner representation of SO8, SO6. And this has charge minus 1. Minus
4 instead of 8.
4 instead of 8. Look at this. Plus minus, plus minus, plus minus. So that looks like 8. But it's chiral. So total number of minuses has to be even.
I see. Okay.
Okay. So the 4 states are plus, 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 minus, 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 plus, minus.
Oh, in the creation itself, there are 4 chiral and 4 antichiral.
In the creation operators, there are 4 chiral, and the annihilation operators have 4 antichiral.
Okay. Now I am asking, what do you call if you have in the creation operator if you have odd number of minus?
Cannot be, because the original spinner, SO8 spinner, was chiral. This is a plus here.
Oh, I see.
So the remaining minuses have to be even in number. Okay? Clear? Go on.
Explain why the vacuum had this charge minus 1.
Charge minus 1? We had the vacuum had charge minus 1 because at the moment you can leave it as some charge A. But you know, in the end we're going to get the space, the state space will be obtained by taking the vacuum, acting on it once, twice, 3 times or 4 times with these creation operators. Right? More than 4 is impossible because they anti-commute with each other.
So then it goes to half, not 1, right?
Wait, let's see. This one, if we start with minus 1, next guy will go to minus half. Next guy will go to 0. Next guy will go to plus half. And then next guy will go to 1.
So you just want it to be symmetrical.
I want it to be symmetrical because otherwise it will be impossible to fit it into an SO8 representation.
But you could have started with any minus.
I could have started with, let's say, minus 2, but then it wouldn't have been symmetrical.
Right. Since you have 4.
Yes. Louder, Sunil?
This vacuum is annihilated by all annihilation operators.
All annihilation operations, by definition. Because we've broken up our operators into half creation, half annihilation. There's always some state which is annihilated by all annihilation. We start with that, we call that the vacuum. Okay? Since that condition is an SO6 invariant condition, the vacuum itself is SO6 invariant. Right? Because the annihilation operators themselves transform in a representation of SO6. It's not SO8 invariant. That's why it has some charge. Clear? Okay? Great. So the first state, so this is what I call level 1. So these states are like just 0. These states are like 1 Q plus, one A dagger on 0. One creation operator on 0. That was for C and charge minuses. Clear? Now what about the next state? Next step. Now we act with 2 creation operators on the vacuum. First tell me what its U1 SO2 charge will be. 0. Next tell me how many states there will be. 6. Excellent. 6. It will be 4 into 3 by 2. Okay? Now we have to identify what this 6-dimensional space is. It's a vector. Pretty clear, right? You've got SO6, you've got a 6 type. But how, it's probably the unique 6-dimensional representation of SO6. But suppose you're not satisfied with that. Maybe a situation where you're doing this kind of algebra where there are 2 6-dimensional representations. You want to know which one. How do you figure it out? It's very easy. So I'm just going to show you very clearly. Look, in this, of course, there are many more sophisticated ways to work. But often it's best to work with your hands. Okay? And look, so what were the chiral spinor states? I'm leaving out the halves. They were plus, 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 minus, 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 plus, minus, and minus, minus, plus. These were the 4 chiral spinor states. Now we act with 2 of them on the vacuum. No 2 equal because they're antisymmetric. So states we get are by pairs of no 2 equal guys acting on vacuum. So let's just work out the charges of all of the pairs. Let's start with this guy with this. Clearly that has 1, 0, 0. Because plus and plus add, they were plus halves. So it becomes 1. But plus and minus cancels and plus and minus cancels. Then I pair this with this. That gives me 0, 1, 0. Then I pair this with this. That gives me 0, 0, 1. That's 3 of the states. Now what about the remaining 3 of the states? Now I have to pair, let's say, this with this. Plus and minus cancels here, plus and minus cancels here, but minus adds up. So we get 0, 0, minus 1. And similarly, the others will be minus 1, 0, 0, and 0, minus 1, 0. As you can check, pair this with this, or this with this, and you'll get these other 2. Okay? But these indeed are the weights of the vector representation. Right? Because the vector is a representation in which under each 2-plane rotation, the charge is either plus 1 or minus 1. And everything else is neutral. That's what we see. Clear? It's a simple thing to check what representation you get because it's easy to enumerate all the charges of the states you get. Okay? So clearly this guy here was 6 vector. Is this clear? Okay. Now, what about the next guy? How many states will there be? 4. Good. What will the representation be? Okay, first U1 charge. Here? Half. What will the represent? There's 4 here. What? Antichiral. Excellent. Correct. Antichiral. How do you know? You could work it out. But what?
Charges will be minus.
Yes. Yes. The easiest way to argue this is to imagine now that you started not from the vacuum but the anti-vacuum. Now the role of creation operators is that of annihilation operators. But the annihilation operators transform in antichiral representation. So these are the states created by acting on the anti-vacuum by the annihilation operators. Anti-vacuum is as invariant under SO6 as a vacuum was. So clearly it's now in the antichiral representation because the annihilation operators transform in antichiral. Is this clear? Okay, so that's for antichiral, and then finally we reach the anti-vacuum. Clearly this is 0, -1, +1. All good? This is our state content of quantizing this spinorial Clifford algebra. Quantizing the spinorial Clifford algebra, but under SO6. We want the state content under SO8. That's when we can declare victory. Okay? We want the state content under SO8. So what do we do here? Well, you look at it. First you have, let's look at these two guys together. 4C with a -12 and 4A with a half together combine into one particular SO8 representation. Can anyone tell me which? Antichiral. Excellent, Prakshu. You see, because an SO8 antichiral representation is just any combination of plus minus, plus minus, plus minus, plus minus, such that the total number of minuses is odd. But if we break that up into SO6, if this guy was +12, this has to be antichiral, because the total number of minuses has to be odd. But if the guy was -12, this has to be chiral, because one of the minuses is already here. So we should but we're saying that -12 goes with chiral and +12 goes with antichiral. And so what we've got is 8A. So those guys combine up into 8A.
Sorry, how is it antichiral?
Because 4C was a representation with, let's say, so 4C was this guy. These were all the states of 4C. Okay? But now if we're interested in SO8, we have to include also this charge. So the states become plus, 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 minus, plus, minus, 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 plus, minus, minus, and minus, minus, plus, minus. Clearly antichiral. What about 4A? That would be the guy with odd number of minuses. But the last guy there is plus. So it will remain odd number of minuses. Okay? So we've combined the 4C and 4A into an 8A. That's good. Okay? Now, what about the rest? 8 vector. Excellent. You see, we've already worked out the charges of these guys. Let's upgrade them to SO8 charges. All of these came with SO8 charge 0. So these, when I upgrade it, this becomes 0, 0, 0, 0, 0, 0. I just put a 0 at the end of each of these. But if you look at 0 minus 1, that is the state which is 0, 0, 0, minus 1. And look at 0 plus 1, that is the state which is 0, 0, 0, plus 1. Together, these form the charges of the SO8 vector. Okay? And so we've concluded that, conclusion. Spinorial. Clifford algebra of SO8, of SO8 chiral. Okay, the state content is equal to 8 vector plus 8 antichiral. Okay, this is a physically interesting situation because I'm looking at the case of one supersymmetry in 10 dimensions. One chiral supersymmetry of 10 dimensions. This is the amount of supersymmetry that is the largest amount of supersymmetry we can have in a theory without gravity. Remember, we discussed last time the largest amount of supersymmetry you could have in a theory without gravity is 16 supercharges. Okay, and 16 supercharges is what we have. 16 supercharges is what we have because we were looking at supercharges of SO10, spinors of SO10. Naively, that would have been 2 to the power 5, which is 32, but we're looking at chiral, so that's 16. And you see how it works, right? We've produced vectors, so spin 1, and we've produced spinors, but we've not produced anything with spin larger than 1, which was our criterion for having a theory without gravity. Indeed, this is the state content of 10-dimensional, 9 plus 1 dimensional Yang-Mills theory, supersymmetric Yang-Mills theory, with one with the only number of supercharges you can have if you have only Yang-Mills theory. Okay. Now, this Yang-Mills theory, 9 plus 1 dimensional, dimensionally reduced down to 4 dimensions, is n equals 4 super Yang-Mills theory. So it's also state content of n equals 4 super Yang-Mills theory, though that would be said in different words because we've represented in representations of SO8. There we would take that SO8 and make it some SO4 or something else. Right? Okay, but it's also that same state content. Okay, in terms of 10-dimensional Yang-Mills theory, n equals 1 Yang-Mills, I don't know what people call it, 10-dimensional super Yang-Mills theory. What is this field? It's the gauge field. It's the gluon, right? And this is the gaugino. Okay, so this is the simplest supermultiplet of a theory with n equals 1 in 10 dimensions. Its two fields are the gauge field and the gluino. All good? Let's do one more slightly complicated example, one more complicated example in 10 dimensions. Let's just double the number of supersymmetries. Okay, let's double the number of supersymmetries. So this is the maximum number of supersymmetries we could have in a theory with without gravity. But you remember 32 was the largest number of supersymmetries you could have in a theory with the gravity. Okay, so we could do either type 2A or type 2B theory, the chiral one or the antichiral, the non-chiral one. Somebody choose, A or B. B. Okay. So let's do that. Okay. In that theory, in the theory that Sunil has chosen for us, we have two supersymmetries, both of the same chirality, under SO10. Okay? So, the descent is the same as what we have here. That is, we choose the Q pluses. Only Q pluses are active. Everything is the same. The only thing that's different is that now we've got two flavors. Okay? So let's write it down just to be clear. Our Clifford algebra is made up of SO8 charges, SO8 spinors, which were chiral, but after C alpha beta times some P plus, which we'll absorb into normalization. That doesn't matter. Right? But in addition, there is an IJ label here. And there will be like a delta IJ. Remember this dimension, the R symmetry, was SON. These indices are real indices. They're real vector indices. We don't have to keep track of up and down here. All okay? So now we want to look at this Clifford algebra. Okay? Once again, we can choose our charges. Now we've got, so what have we got? We've got two chiral SO8 spinors. Once again, we choose the charges to be broken up into creation and annihilation. Okay? Once again, we can choose those creation and annihilation charge guys in the way we did before. That one of the SO2 charges plus means, what did we say? Creation. Yeah, plus was creation and minus was annihilation. Only difference is that there's this additional label. Okay. Now, for this SO2, let's keep track of, I mean, just for fun, it's not very important, but let's keep track of this SO2 charge also. This R symmetry SO2 charge. Okay? So we will label the Q's as Q plus and Q minus. Now, this shouldn't confuse you. This now is SO2 R symmetry. It has nothing to do with the pluses that we had up there. Plus under that SO2 is always plus. Minuses are just not there. I hope this won't confuse you, and I'll continue to use this notation. Is this okay? Okay, excellent. So we've got Q plus and Q minus. And now we need to choose our creation and annihilation.
Just to remind, Q plus is it like Q1 plus IQ2?
Yes, Q1 plus IQ2 and Q1 minus IQ2 but this is 1 and 2 under SO2, R symmetry SO2. Nothing to do with the spinner. This is spinner labels. Okay. Now, let's see. Now we have to break up our operators into creation and annihilation. And, in this case, it's very tempting to do the following. In this case, maybe we can just do it always SO8 covariant. How about choosing the Q minuses under SO8 to be annihilation, and Q pluses under SO8 to be creation? I think that's fine. Okay, so remember that the thing here, this commutation relation, will only click with a plus and a minus.
Sorry, just another
Please.
question. This SO2 has nothing to do with this SO8.
Nothing to do with this. SO8 was,
It's inside that.
it's an internal symmetry. Nothing to do. It's R symmetry. Okay? And if we were, we needn't really have kept track of that. But look, the point is to break up the operators into creation and annihilation. But you only get clicking between a plus and a minus. So it's already broken up for us in some way.
Here, individual Q had this structure.
Yes?
But now you have already this plus minus structure. That's why you are not going in.
Yeah, we need to, the point of creation and annihilation operators is that the creation and annihilation operators have non-zero pairing. Okay? We broke it up last time saying that pairing only happens across equal and opposite charges. So we chose one charge, namely SO2 and in one of the two planes to be that equal and opposite. Here we can do it more nicely. We can choose that charge to be the SO2 charge, the R symmetry charge. Okay, so let's go. In this case now, our creation operators are all of Q plus. Now plus was charged +1 because this was a vector type R symmetry. You know, the other SO2s had charges minus because we were dealing with spinors, but under R symmetry it was a vector. How many creation operators do we have now? Eight. Excellent. So we have 8 creation operators now. Okay. So we're going to take our vacuum state to have charge under R symmetry. -4. So that when we act 8 times, so when we act 8 times, I hope I got that right. Yeah.
There are 8 gaps.
8 gaps, exactly. So we'll go to +4. Okay. And now the SO8, we can keep track of full SO8 type. Okay, so it'll be easy. So let's try. Okay, so first there is the vacuum, which is SO8 0. Here now this is keeping track of full SO8 charges. When the next state is, the next state clearly is what representation of SO8? Yes. So this is 8 chiral times R times -3. Okay. Next, we have the product of 2 chiral. The next step, we'll have the product of antisymmetric product of 2 chiral spinors. Okay. So antisymmetric product of 2 chiral spinors. Let's see what that is. Okay. So in the antisymmetric product of 2 chiral spinors, the antisymmetric, okay, I'm going to give you a prediction and then we will check it. I'm going to claim that the representation we will get will be 8 into 7 by 2, which is equal to 28 dimension, 4 into 7, right? So we will get a single 28 dimensional representation and we'll identify it. Okay, so let's see what kind of representation it is.
Sorry, what is the structure of this Q plus, like this plus minus or plus minus?
Q plus is a chiral spinor. Okay, so it has 8 charges. I'll write them down.
All of them are combined right now.
What? All of them are together. But let me write them down once, just to be totally clear. Okay, these are all that there are, with first guy being plus, is that right? I think so. So the first guy now has become minus, but let's say second guy is plus, then we need 1 minus. Plus minus. That's all that we have with second guy plus, so then we have second guy also minus, and then we could have plus, or we could have minus. 1, 2, 3, 4, 5, 6, 7, 8. All of these have positive charge under R symmetry. Yes?
Wouldn't this anti-commutation click even when we have like this kind of clicking, but the charges are opposite? That SO2 charges. That is not included in this, right?
Wait. Say that again.
So there will be one more kind of clicking where we had similar which we
No,
had here.
all charges have to be opposite for it to click. It's not one kind.
One plus will have plus charge and minus charge for the R symmetry.
We'll have plus charge and minus charge under the R symmetry. Correct? Yes? Yes. So this guy will click. This guy is always with plus here, right? All of these are. And the annihilation operator is the same thing, but with all of these replaced by minus. So this guy will click with the partner of this guy. Each one has a partner with whom it will click. Okay, all charges have to be reversed for the clicking, because the commutation relations are invariant under SO8 times SO2. Okay, so charges have to add to 0 if something clicks. Clear? There is only SO2. There were two charges. In this dimension, our symmetry was SO n plus times SO n minus. So it's SO2 times SO0. Okay, excellent. Now let us see. Okay, first that you get 28 states here is clear, right? Because it's pairs of 7 times 8 by 2. Okay, and let's try to understand roughly what the states are like. Okay, look at this guy. This with this. That gives us 1, 1, 0, 0. Okay, let's take another random pair. Let's take this with that with that. That's interesting. Oh, is there a, maybe there is, Yeah, of course there is. Yeah, let's take this with this. We get a 0, 0, 0, 0. Okay, or let's take this with, I don't know, let's choose any two. Let's take this with this. You see we're going to get, in this case again we get 0, 0. So always we will get either 2 pluses or 2 minuses, maybe 1 plus 1 minus, or all zeros. Okay, can anyone identify the representation from that? Okay.
Symmetric of vectors, 2 vectors.
Antisymmetric of 2 vectors. You see, had it been symmetric of 2 vectors, we would have had a state which was 2, 0, 0, 0. Right? Also, had it been antisymmetric of symmetric of 2 vectors, its number would not have been 8 into 7 by 2. 8 into 9 by 2 minus 1. Trace removed. Right? Yeah. In this case, if you look at it, you will see that basically what we're getting is everything that you can make by antisymmetrizing 2 vectors. The 0, 0, 0, 0 came by antisymmetrizing 2 vectors that had equal charge. Right? You had a vector which was 1, 0, 0, 0. There's another vector component which is minus 1, 0, 0, 0. Antisymmetrize those, you'll get 0, 0, 0. And you'll get them many times because you can antisymmetrize this guy or the guy with 0, 1, 0. You know what I mean, right? Of course, all this can be done more seriously. But we will get this 28 dimensional space. Okay. Now, just because we want to connect with what we know, I'm going to give this a name. I'm going to call it B mu nu. Okay. Great. Next, keep going. I will keep going only. Okay, fine. Let's keep going. At least one more. Okay. Next we get 3 of these. 8 into this chiral into chiral into chiral. Okay. It's clearly well, how many states do we get this way? We get 8 into 7 into 6 divided by 6. This is equal to 56 states. Okay. Now, this time we have a spinor type representation because the charges are going to be half odd. Okay. So clearly we're going to get a spinor type representation. Now, let's see what will be the largest charge at any point. Let's suppose we take this, this, and this. The charges in the first guy add up to 3/2.
And you can't, so here you're saying that you have 8 elements.
Yes.
You're choosing 3 out of 8, right?
You're choosing 3 out of 8, and you can't choose 2 equal because they square to 0.
This is making it antisymmetric.
This is making it antisymmetric. Okay? Can you see that the highest charge that you're going to get, highest spin in any one direction, will be 3/2? You'll also get minus 3/2. That's fine. Now, turns out in this case it's a single representation. Can anyone tell me what that representation is called? 56-dimensional representation with spin 3/2. That's it. It's the Rarita-Schwinger representation. We'll write the number 28. And I've got lazy, I've stopped. Okay, I'm going to stop keeping track of this R symmetry charge since it counts for very little. Okay. This was Rarita-Schwinger 56. What is the Rarita-Schwinger representation? Anyone? Rarita-Schwinger is just an object that carries both a vector and a spinor index. It's got a vector index and a spinor index. So you might think then it has 64 components. Because under SO8, a vector index is for 8 components, and a spinor index is also 8 components. So 8 into 8 is 64. And that would have been true if a Rarita-Schwinger had been exactly only a vector index and spinor index. Okay? But it's a bit more.
You're saying it doesn't have same indices.
A Rarita-Schwinger object is something which is psi mu alpha, which obeys the equation gamma mu alpha such that gamma mu psi mu alpha beta. Rarita-Schwinger spinors are defined by, it's a vector type spinor, subject to this additional constraint. This additional constraint is imposed in an SO8 invariant manner. Okay? Therefore, it can be imposed and maintain that it's a representation. So if you just took product of vector and spinor, you wouldn't get an irreducible representation. In fact, if you take product of vector and chiral spinor, you get a chiral Rarita-Schwinger spinor and an antichiral spinor. Why? Because the remaining part is this gamma, and when you take gamma 5 through gamma, it flips sign. So if psi was a chiral spinor, gamma times gamma mu times psi is an antichiral spinor. Is this clear? So this is what a Rarita-Schwinger spinor is, and because it has 8 constraints on 64 components, it has 56 components. Of course, I'm talking only in 8 little group dimensions, right? All these numbers change dimension by dimension. Just doing the dimension we are interested in. Of course, I've chosen this dimension because it's string theory. So we're going to get things that we know we should get. Please.
Sorry, roughly this vector index has 2 spinor indices, right? This is how.
No.
There are 3 chirals and you constructed it and then.
Oh, yes.
2 of them made it to vector.
Yes, but it was not 2 unconstrained spinor indices.
Exactly. So because the one which can be in the one spinor, it can't be present in other 2.
Right.
In the vector.
Right.
That's how you can.
That kind of thing. Yeah, it's true that this Rarita-Schwinger is obtained by acting with 3 spinor indices.
Yeah.
Okay, completely antisymmetrized. Okay, that gives you in the end this Rarita-Schwinger spinor. Okay. Now something that we did not keep track of very carefully here in this case, where were we? Oh, did I rub out? Oh, I rubbed out our charges. Oh, what a pain. Yeah. Well, okay, fine. Let's just. There are two kinds of Rarita-Schwinger spinners. There are Rarita-Schwinger spinners, which is formed by the product of a chiral spinner and a vector. And there are Rarita-Schwinger spinners, which are formed by the product of an antichiral spinner times a vector. And I was going to check which one it was, but I'll leave it, because we've rubbed it out, I'll leave it for you as an exercise.
The one that comes from lowering 3 from the top.
Yes, this one, the one that we've written already, RS. Just check whether it was the thing that you got out of chiral spinner times vector or antichiral spinner times vector. Okay? Right? So the easy way to check that is take the guy with the charge 3/2. That was a spinner, and then one of the vector charges has been added on. You've taken +1 and added it to the half to make a 3/2. Okay, so just check whether that has even number of minuses or not. I'll just check it for you. We had one which was plus, 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 then another which was plus, minus, minus, and another which was plus, plus, minus, minus. Put these three together, we get 3/2. Here we get half. Here we get half and minus half. Did I do it right, people? I think I did. What? Half, minus half. Right? So this clearly came from half, minus half, and adding the 1 from the vector. It's the only way it could have come. So this was an antichiral spinner. So I'm going to call this a 28A. Oh no, not this. The 56A. That is the Rarita-Schwinger spinner that you got as a product of an antichiral spinner times a vector. I'm not sure this is standard notation, but this is what we mean. A means making out of a product of antichiral spinner times vector. Okay? Of course, whether it's chiral or antichiral is always convention. What is not convention is if you have two different things. One is chiral, the other is antichiral. That's not convention. Okay? So what was not convention is that this guy and this guy are opposite. Can you give me an interpretation for why this guy and this guy were opposite? Well, this was precisely. Where did I write it? Where was the this was precisely this object. So what happened was you produce that full object, but it's two representations. The Rarita-Schwinger and the pure spinner, but they have opposite chirality because one of them comes with multiplying by gamma. Clear? Okay, let's move on. Last guy, and then we'll. Okay, let's finish this, since we're going to get the spectrum of type 2b supergravity or string theory. Let's finish it. Okay, so now let's do the guy with 4. Okay, the guy with 4. First, is it going to be a spinorial type or vectorial type representation? I mean, half integers or integers? Integers, excellent. Okay, and this guy, what is its maximum spin going to be? Let's find an example where it's 2. Yes, it'll be 2. Okay, so suppose we do plus, minus, plus, plus, minus, and plus, minus, plus, minus, right? We choose these 4. This guy will add up to 2. Okay, we choose those 4, that guy will add up to 2. Let's check how many states there are in this. The number of states here will be 8 into 7 into 6 into 5 by 6 into 4. Right, 24. This is 28 into, what's a lot? This is 2. Thank you. Yeah. 70. Now, what is this? What is this combination? This 70. So let's, well, one state, one multiplet that has to be here is the spin 2. Is the, somebody say it? Graviton, right? Okay, so we're going to get, graviton is spin 2 is traceless symmetric of SO8. Okay, so it is 8 into 9 by 2. Okay, minus 1. Okay, so this is going to be 4 into 9 minus 1, which is equal to 35. Okay, and now what else is there that makes up that remaining 35? Let's see, 35. What? Say again? Zero charge. That makes 36 maybe. Is that what you want?
So this will have charge 2.
This will have charge 2. Right. This will have charge 2. This will be the spin 2 symmetric represent. It's the traceless symmetric representation of SO8 that includes states with 0 charges, right? Because if you take the symmetric of 1 0 0 0 and minus 1 0 0, so this representation will certainly be there. What else will be there in this thing? Give me 1 minute. So we had type 2. Mm-hmm. 1 minute. 35. I wonder if it is. See, what is the full content of the type 2B supermultiplet? Apart from the spinor and the so let's say this is the vectorial type. Type 2A has a gauge field, so this one has, right. So it's B mu nu, so it's phi and chi, two scalars. Then there's B mu nu and C mu nu. Then there is the A mu nu alpha beta self dual. Let's check this. This number of components are right. So the number of components of this is 8 into 7 into 6 into 5 by 24 divided by 2. The self-duality condition. So we checked that this was 70. So divided by 2 is equal to 35. Okay, so that's what we're getting. What we're getting here is not one representation, but two representations. And I should have known this. You know why I should have known this? Because of triality of SO8. Because of triality of SO8, whatever you get by product of spinors is related to what you get by product of vectors, because vector and spinor representations are related by moves under SO8. Are you familiar with this? So if you take the antisymmetric product of vectors, you get one representation, except if that number, if the antisymmetric product of vectors is 4. Because then you get a 4-dimensional antisymmetric representation, which can be broken up into 2 by self-duality. So antisymmetric product of 4 vectors gives you 2 representations rather than 1. So once again, you should have expected that antisymmetric product of 4 spinors by triality gives you 2 representations rather than 1. Are you familiar with triality, people? No? Triality is the statement that in this one very special group SO8, in this one very special group SO8, what you call vector spinor and chiral spinor is convention. You are able to perform an automorphism to change your charges, okay, that rotates between vector spinor and chiral spinor. So in this one very special group, for instance, the first paper I ever wrote was to classify representations of supersymmetry algebras, superconformal algebras. After writing it, I got a polite mail from a prominent Korean physicist whom I will not name, who said, very interesting paper, but have you checked whether your paper is consistent with the recent paper of Seiberg? Now, Seiberg was my advisor. He'd been supervising the project, so I didn't even bother. I wrote back, said, yes, consistent. So he wrote back saying, you must be an idiot, because in his paper, the spinors transform under a vector of SO8, and yours they transform under a spinor of SO8. What you've done is clearly nonsense. So this really panicked me, and then I wrote back one word. I said, triality. Because it's the same. But I, of course, actually knew I had to be right, because, Seiberg was, he would have told me if it was wrong. I was totally sure. But we can often get confused in this game. Okay? So this is why you knew before, I should have known beforehand, that when I take the product of 4 spinors, I won't get 1 representation, I'll get 2. Which one? You have to work out the triality map. That's sometimes hard to do in your head. But we should have expected 2, and the 2 are the graviton and this self-dual 4-4. Is this clear? What? In the self-dual, all antisymmetric and self-dual. Right? You use the epsilon tensor to make an equation. You understand what self-duality means, right? Okay, so this guy at level 4 here.
And it was 8-dimensional, that's why it would have made sense.
Because it's 8-dimensional, it makes sense. Self-dual, SD 4 index. Is this clear? Okay, excellent. Okay. Right. Now we can keep going. Can I leave it to you to finish this? We could keep going to the 5, 6. Actually, the easiest way is to do it from the other side. Okay? We could start doing it now from the other side. Okay? Now the other side, unlike in the previous case, the other side is not as far as SO8 concerned, opposite. And let's finish it actually, because we can just do it from the other side. So from the other side, when we do it, you see, because both spinners, R symmetry plus and R symmetry minus, were both chiral spinners as far as SO8 was concerned. Right? So when we do it from the other side, the SO8 charges will be the same. Okay, and let's keep track of this. This was -1 and this was 0 for SO2 charges. All that will flip is the SO2 charges. Okay, so can you see we will just get 0, 4, we will get 8 chiral, 3, we will get, let's call it A mu nu, 28, 2, we will get RS 56A, which is 1, and that's not a second guy, that was unique.
Will it be chiral?
No, nothing has changed.
Oh yeah. SO8 is same.
SO8 is same. This is the point. Type 2B theory has 2 Rarita-Schwinger spinners of the same chirality. Type 2A theory, on the other hand, has 2 Rarita-Schwingers, one of positive chirality and one of negative chirality. Okay? Clear? Okay? This is exactly the type 2B supergravity spectrum. Right? The type 2B supergravity spectrum includes a dilaton and an axion, 2 scalars. It includes 2 Rarita-Schwinger spinners of the same chirality and 2 ordinary spinners of the same chirality but opposite that of the Rarita-Schwinger. It includes two form gauge fields. One of them is B mu nu, the Karl-Bromond B mu nu. Second one is the one that couples to the one brane. It's a Ramond-Ramond field. It's the gauge field for the one brane. Okay, and then it includes the graviton, and then the field that couples to the 3 brane. The 4 index field that couples to the 3 brane. This is self-dual. Notice that in this theory there is a doubling of all fields except the graviton and the self-dual field. This doubling came from starting from top or starting from the bottom. This doubling, as you know, is very consequential. It's the first sign that this theory actually has S-duality. Okay, under S-duality, fundamental strings and D strings are interchanged. So B mu nu and A mu nu are interchanged. Okay, and so on. Of course, that is not the topic of today's lecture. The topic was just group theory. What I want to convince you in today's lecture by the end is that this is extremely simple and extremely powerful. Okay? So, the supersymmetry itself, as you've now seen, quite complicated examples. Supersymmetry itself ensures that you cannot have fields appearing by themselves. If you have n equals 2 supersymmetry in 10 dimensions, the minimum massless content is what we've listed here. These have to appear. More could happen. Because what we're assuming is that in this, the representation of n was the trivial one. So that there was no further Clebsch coordinating. And that correctly gives you the representations here. The point was that had you chosen something non-trivial here, you would have got spins larger than 2. So in the case of n equals 2 supersymmetry, for massless representations, you don't want to choose something more non-trivial. Okay? So what I wanted to convince you, so all these things have names, by the way. Okay? This will be called the n equals 2 gravity multiplet. The one we got out here would be called the n equals 1 vector multiplet. Okay? When you're studying supersymmetry or you go to talks on supersymmetry, you will often be told, we're studying a theory with a vector multiplet and 3 hypermultiplets. All those words have meaning as we have their particular representations of the form that we have explained here. Strathady's paper, the one we are following for these last 3-4 lectures, has a complete listing of the state content of all representations with spins less than or equal to 2. Okay? So all you're doing when you look at those multiplets is looking at one of these things. Is this clear? Okay. Maybe the last thing I should do when okay, fine. I think we'll stop our discussion of massless representations here. I wanted to explain how representations can become BPS when they are massive. That's perhaps the last thing we should do in our discussion of discussion of representations, and then move on. Okay. Any questions or comments about what we've been discussing? Is what we're doing clear? Is the logic clear? The algebra, you see, it's very easy, right? That's what I wanted to convince you of, that this representation theory is very easy. You can just do it by hand for any case you're interested in. Okay, fine. Okay, let's look at a massive representation with a central charge. So can somebody help me with the three-dimensional supersymmetry algebra we wrote down, including, the very explicit form we wrote down at the end of the last class? We had, what was it? Qi plus Qi minus Qi plus was equal to P plus times something. Is it possible? We had it on this side of the board last time. What? This J P plus times delta I J. Was there a 2 here? 2 minus I Q minus J is equal to 2 P minus delta I J, and Q plus I Q minus J minus P3. And where did the Zij come? Okay, P0 plus P1 by 2. Okay, so let's just define it as without so the big. Okay. Perfect. So let us now look at what?
D is equal to 3 or
This was D equals 3, right?
yeah.
This was D equals 3. And so first, now total number of supercharges. So suppose n, this ij ran from 1 to n. And suppose n was equal to 2. Okay? In this case, the total number of supercharges, well, there are 2 q pluses and there are 2 q minuses. So total number of supercharges is 4. Okay, so total number of charges, let's in general, total number of charges is equal to 2n. N equals 2, for instance, equals 4, implies 4. Okay, now let us look at the case where we've got a massive field, massive representation. Okay, so we orient it so that our particle is at rest. Okay, so P plus and P minus are both equal to each other and they're both m, and P3 is 0. So we've got plus j. Okay, now let's focus on the case n equals 2. Let's focus on the case n equals 2. This is the first place something non-trivial will happen. We'll focus on the case n equals 2, and oh, and by the way, in this dimension, Zij was, I suppose, anti-symmetric, right? I'll check this. If somebody can find it in their notes, you might find it faster than me. No. Yeah, Zij is antisymmetric in 3 dimensions. Okay, excellent. So we focus on the case n equals 2. So we have z plus minus is equal to minus z minus plus is equal to, let's call it z. Okay. And once again here we will put, we will work with R symmetry charges plus and minus, like we did for, right? So we have here plus minus, okay, is equal to P plus.
Sorry, now you are doing
n equals 2. Okay, bottom indices are spinor indices. Top indices are R symmetry indices. Okay, so Q, okay, and everything else is 0. Right? So Q plus plus Q plus plus is equal to Q minus plus, minus plus is equal to 0 because delta ij doesn't click. Okay, similarly we have Q plus minus Q plus minus, sorry, minus is equal to P minus and rest 0. And we have Q plus Q plus plus Q plus minus is equal to Z. Minus is equal to Z. This is our algebra that we're interested in quantizing, finding a representation. What was it? There is one?
Is Q plus minus with Q minus plus?
Q, yeah, good point. So this is non-zero, and Q plus minus with Q minus plus. This is what you were after, Takshu? So, P3 is 0. We're going to a frame where P0 is the only momentum. Right? So P0 is the only momentum. Rest frame. So P plus and P minus have both become mass, I should have. Okay? Excellent. So let's so let's look at this. Okay. Now, I want to convince you that there is an inequality relating M and Z. Give me a minute to see how that comes about. Okay. The first thing we need to know is what the dagger relationships are in this algebra. Now, and we will use positivity. Exactly. What we will do is to, find an operator, some anti-commutator of an operator and its dagger. That will have to be positive, and that will give us some inequality. Okay, so we understood this last time. Dagger flips every sign of charge except the plus minus that includes time.
Yes.
Do you remember that? Because of the extra factor of I, the plus minus that includes time is not P1 plus I P2. It's P0 plus P1. So it doesn't get flipped by dagger. Okay, we saw that explicitly in some example. I can't remember which one. You remember this, right? So the rule then is that under dagger, this guy and this guy are daggers. Okay, similarly, this guy and this guy are daggers. Okay, but dagger doesn't mix up these two. Okay, so let's write these relations in terms of the following. So let's define Q plus, let's call this just notation. I'm calling this Q plus. Let's call this theta plus. Okay, Q plus minus, this will be equal to theta plus dagger. Okay, and Q minus plus we will call theta minus, and Q minus minus we will call theta minus dagger. Yes? Yes?
In the first one, at least RHS is delta Ij, right? Then you should
Delta Ij, but delta Ij was R symmetry delta Ij.
yeah.
So with plus and minus, plus minus is 1. Is this confusing?
Yeah.
Plus minus means moving to the basis 1 plus I2 by square root 2. Okay? So it's the same algebra as the following. Consider Z is equal to x plus Iy, and Z bar, Z is like plus. This is like 1, this is like 2. And Z bar is equal to x minus Iy. Okay? Delta Ij was the metric dx squared plus dy squared. This becomes the metric dz bar. Plus and minus clicks. Is it clear? Okay, in 1 plus I2 and 1 minus I2, plus and minus have to be equal in delta Ij.
And in the last two, we should get Z is anti-symmetry.
Correct?
And we are still using plus and minus.
That plus minus is
That plus minus is constant.
spinner plus.
No, I think he means this one.
R symmetry.
He means this one.
R symmetry.
This plus and this minus gives 1. This is what you're objecting to, right? You see, let's take the epsilon ij and ask what it becomes in z bar basis. Okay? We get epsilon z bar equals 1 and epsilon z bar z equals minus 1. You see, in 2 dimensions, both the completely symmetric invariant and the completely antisymmetric invariant click only between z and z bar. Because charges have to add to 0 if something clicks. Okay? The difference between them is that the completely symmetric invariant has both z bar and z bar z both equal 1.
That's why we had
Only one thing there. Whereas the completely antisymmetric guy gives 1 with a 1 and 1 with a minus 1. Okay? You can easily check this. Okay? Great. Right. Excellent. Excellent. So now we have this, now that we have this dagger will flip R charge, yes, because dagger is complex conjugation. Complex conjugation flips all Hermitian charges. Right? So, for instance, if you have a field phi, let's say chiral superfield, has some R charge, its dagger at minus that R charge. Yeah, I think that's it. Was there something? Okay, fine.
So this charge under SO3 is not changed because it is boost kind of.
Exactly, because you see what's happened is that it was like a 1 plus I2, but 2 has become itself I times something. So it's 1 plus 2. 1 plus 2 doesn't get flipped under. Right? But we saw that explicitly last time while doing spinor algebra. Right? We explicitly checked that this is the one thing that does not flip under. We saw it by looking at, that gamma 0, psi star. See, that extra factor of gamma 0 is what restored it. Okay, we explicitly checked that. Had to be, but we explicitly checked that. Okay. So, great. Now, what I want to do is to choose a clever combination of a charge and its dagger. Okay, so the most general charge is alpha plus theta plus alpha minus theta minus plus alpha plus star, something, alpha plus tilde theta plus dagger plus alpha minus tilde theta minus dagger. Okay, and the complex conjugation of this, this commutator with alpha plus star theta plus dagger plus alpha minus star theta minus dagger plus alpha plus tilde theta plus star plus alpha minus tilde star theta minus, this has always to be greater than or equal to 0, right? For any choices of alpha plus, alpha minus, alpha plus tilde and alpha minus tilde. Just because what we're doing is considering the anti-commutator of an operator with its dagger. Okay, this is a positive definite thing because it's sum of two terms, each of which is positive definite. Okay? Now, I want to use this thing cleverly Give me 1 minute to see how I should use it. Okay, fine. Let us first. Okay. Now, this has to be positive definite. This means that the 4 cross 4 matrix that we form from this with this has to be a positive definite matrix. What? Right, has to be a positive definite matrix. So let's just write down this 4 cross 4 matrix. Okay, so let's. Right, we will write down the coefficient of alpha star. Right, so that will tell us that this matrix has to be positive definite. Okay, but we can now write out that matrix because we know all the commutation relations. So I'm just going to write it out and then we will draw conclusions out of it. Okay, if I was a bit cleverer, I could have cleverly chosen the right component. But since I'm not, I'll just write out the whole matrix.
Theta is that if I should take theta to be an addition, then theta dagger will act like a creation, right? Causal commutational relation.
Correct. Theta, if we want to create a representation, we can choose that. Yes. But before actually creating representations, I wanted to show you a particular fact. The fact is this thing called the BPS bound. Okay, that's where I'm heading. Okay, so let's just write down this 4 cross 4 matrix where row is this side, column is that side, and here we are where you in the basis plus minus plus dagger minus dagger plus minus plus dagger minus dagger. Okay. So what I mean is this and its complex conjugate. So alpha plus star. So this is theta plus with theta plus dagger. This first element here. Okay. Theta plus with theta plus dagger was M. Okay. Next element is theta plus with theta minus dagger. Okay. And with this is minus, so theta minus dagger. Theta minus dagger was Lipu in the middle of class. Can I call you later? Yeah, tell him if he can wait for 15 minutes, I'll go and pick it up. Yeah. Perfect, thanks. Yeah, bye. Sorry. Okay, sorry. You'll have to help me get this matrix straight.
I think the last element is J, is it?
Let me check. Last element meaning this one?
No, this row.
This row? So, plus with wait.
First element is theta plus with theta plus dagger.
This one. Right, so that's M. Let me get the second element. That's theta plus with theta minus dagger. Theta minus dagger was
Opposite. So theta plus with which one is non-zero?
Right. Sorry, but help me. This one was 0 or not? Theta plus with theta minus dagger? No, it's Z, right? And let's check whether it's plus Z or minus Z. Theta plus with theta minus dagger. Correct. That our daggers were the guys with minus up. Yeah. So that was Z. Thank you. Okay. Now what about theta plus with this theta plus? That of course is 0. Right. And with theta minus, theta plus with theta minus was, that will also be 0, right? Any theta with the theta is always 0 because both of them have plus charges, R symmetry plus charges. Our definition was daggers had minus charges and you only have non-zero commutations between plus and minus, right? So we got, right, perfect. 0. You agree with this? Okay, excellent. Alphas are what multiply this. So this matrix multiplied by, let's say, row of alphas and column of alpha stars is this quadratic form, right? Alphas could be anything. This matrix has to be positive definite, right? Okay, so this matrix has to have only positive eigenvalues, right? Because otherwise you'll be able to choose some alphas to pick out that negative direction. Okay, let's keep going. So now we will choose theta minus. So you people help me again. This is minus z. This is m and then 0, 0. Right? Now I presume we're going to get 0, 0, 0, 0 here. Okay? And now let's get these other guys straight. Theta plus with dagger with theta plus, yes, that's m. I presume this will also be m. And now this theta plus here with theta with this guy, theta minus, this is some z. Help with sign somebody, theta minus z, and this is presumably then a z. Okay, great. So you see what we've got is a matrix here that has to be positive definite. Okay, now this matrix was block diagonal. So each block has to be positive definite. Okay, in particular, the determinant of this matrix, oops. Oh, okay, maybe it works. Fine, not determinant. Let's just work out the eigenvalues of this matrix. So this matrix here is m times identity minus I sigma 2 times z. Or let's just work out its eigenvalues. That's easier. So m minus lambda squared plus z squared is equal to 0. Okay. So m minus lambda squared, something's wrong, right? Something's wrong because this matrix is not Hermitian. Shouldn't the matrix automatically have been Hermitian? Because I was doing something with its dagger. These minus signs of z's, please help me with again. This guy here, let me check these minus signs of z's. Minus with this with this. Theta plus, let me say, the ones we wanted were theta plus. I want it to be symmetric, yes. I want it to be symmetric or to have an I. Oh, maybe there was an I.
It's already a problem with the commutation relations there.
Right. Right.
D is equal to 3, you said it
Right. But in going to, maybe this was the answer to. Let's do this thing more seriously. There's an I. You see, suppose I have dx dy.
I did.
Right. And I want to look at how it goes to dz bar. Okay, dz bar is equal to I minus 2I dx dy. Clear, right? Because you'll get one dx and one dy, and there's an I. So sorry, my answer to you was incomplete. It's true, it was plus and minus, but there was also an I. So, and this also answers Siddharth's question, right? Because the I will presumably fix what you wanted. Thank you. So now this is clear. Now this is I and I. Okay. And now it's very clear. This is just Z times, so this matrix M, so the matrix is M times identity plus IZ times sigma 2. Okay, its eigenvalues are M plus minus Z. Okay, and unless M is greater than Z, unless M is greater than or equal to Z, we have trouble because one of the eigenvalues goes negative. Okay. I could have got the sign of this, this might have been plus I, this might have been minus I, you can check all that. That under Z goes to minus Z, that doesn't change anything, right? Important thing is the relative sign. Okay? And so we see that it's impossible to get unitary representations of this algebra unless M is greater than or equal to Z. Is this clear? This is called the BPS bound. It tells you that when you have non-zero central charge, when you are dealing with the massive theory, firstly it tells you that when you have a non-zero central charge, mass cannot be 0. Because 0 is not greater than or equal to. This is, by the way, mod Z, I should have said, right? Because there was a plus minus here. So M is greater than or equal to mod Z. If Z was non-zero, M cannot be 0. Okay, so that's why when we were looking at massless representations, we always looked at 0 central charge. Because it would have violated the BPS bound. We wouldn't have acceptable representations that were massless with the non-zero central charge. Okay?
But with 0 central charge, you can have massive.
With 0 central charge, you can have massive representations. But if you have a central charge, you necessarily have to have a mass and a minimum mass. Yes. And that mass is set by the central charge. Okay. Now, what happens at the place where M is equal to Z? Where M is equal to Z, then one of these eigenvalues is equal to 0. So that linear combination of charges and its dagger anti-commute to 0. So they have to be represented as 0. Just like when in our discussion for massless the massless representations. Okay? So if you have a massive supercharge, okay, see, now the representation theory of this algebra becomes really clear. What we do, so now let's quickly discuss this. Fine. So first we understand this BPS bound, right? That if you have you have a central charge, mass has to be greater than or equal to that central charge. Okay, otherwise representations are not possible. Also, if mass is exactly equal to, something special happens. Now, what is that special thing that happens? Well, what we can do is now move bases of these central charges, of these Qs. Once we change our basis, we can diagonalize this matrix. Okay, so in the appropriate basis, okay, in the appropriate basis, this matrix of anticommutators, will become m plus z, m minus z, m plus z, m minus z. Now we have two cases. Case 1, mod m is not equal to mod z. It's greater than mod z. In that case, all 4 of these integers are positive integers. Now we can take those supercharges in whose basis this is the right algebra and normalize them like we normalize the supercharges with a factor of p plus for the massless representations. So that after that normalization, what we will get is 1, 1, 1, 1. In this situation, now we have a Clifford algebra. Okay? In this situation, we have a Clifford algebra with 4 effective gamma matrices. We'll make 2 of them creation, 2 of them annihilation, and we will get a 4-dimensional, the representation space will be some 4-dimensional space, whose charges we can, if we want, work out under SO2, both R symmetry as well as the SO2 rotations that are left over. Left over because now our little group is SO2, not SO1, because we've got massive representations. Okay? Well, this would be an easy exercise to do. The point I want to emphasize is the following, that if m is equal to mod z on the other hand, let's say m is equal to minus z, then this guy and this guy are 0. Then those guys are not represented at all. And now we've got a Clifford algebra with 2 gamma matrices and a 2-dimensional representation space. So you see that the representation theory of massive representations depends crucially on whether the BPS bound is saturated or not. In the case that it's not saturated, typically massive representations are bigger than massless representations with the same amount of supersymmetry. Okay? Because massless representation, if you have 4n supercharges, 2n of them are inactive for massless representations. And then we make them n annihilation, n creation, and you get a 2 to the power n dimensional representation. Okay? For massive guys, if you have 4n supercharges, typically none of them are inactive. So you have 2n creation, 2n annihilation, and you have 2 to the power 2n dimensional representation. However, in the case of BPS representations, and I've only shown you the simplest BPS kind, sometimes sub-BPS, where, anyway, in the case of this kind of BPS, some supercharges become inactive. In this case, as many became inactive as would have happened had the theory been massless. Okay? So it goes from a 4-dimensional representation to a 2-dimensional representation. Okay. Now, BPS states are very crucial, BPS representations are very crucial element of control in supersymmetry. Because as you see, a BPS representation is one in which one of the supersymmetries, the one whose linear combination is that eigenvalue, annihilates the state. Right, because it's represented on this multiplet as 0. Clear? So BPS representation is a representation in which some of the states are annihilated by supersymmetry. Massless representations are always a special case, because some of the supersymmetries, namely the Q minuses, annihilate the state. Okay? So So massless representation is always BPS. But you can also have massive representations that are BPS. Now, the reason that BPS representations are sort of dynamically special goes as follows. BPS, in this context, it's a particle whose mass is equal to its central charge.
If you have multiple central charges.
If you have multiple central charges, then you have more complicated such algebras. Whenever an inequality is saturated,
There are multiple inequalities.
there could be more than one inequality. There could be interesting kind of things, right? We've looked at the simplest case.
But you have to take the most stringent one.
When any inequality is saturated,
Okay.
some supersymmetry annihilates the state.
Mathematically it is true because it will shorten.
It will shorten. That's all we care about, right? There are half BPS states, there are quarter BPS states. We will see some of this as we go. Okay. Now, why is it important that things are BPS or not? It's important for the following reason. You see, in a normal quantum field theory, if a particle has some tree-level mass, some mass in the classical Lagrangian, typically its mass can be renormalized. Interaction effects renormalize its mass. Now, if you have a BPS particle, and you know for some reason that its central charge is not being renormalized. In the very simple special case that I showed you, the central charge was central charge and a charge under SO2. And SO2 charges typically can be renormalized. However, if you had SO3, if you had one more supersymmetry or higher, so those charges cannot be renormalized. Can anyone tell me why? Cannot be continuously. The statement. Exactly. Who said that? Siddharth. Very good. Perfect, Siddharth. Because they're discrete. So the statement is this. Suppose you have a classical theory or some point in the moduli space of quantum field theory. So you've got, but let's say a classical theory, in which you know the charge assignments of various particles, let's say. Okay? And I know that one of my fields, let's say, has SO2 charge half. Question, could it be that under SO2, that the SO2 charge becomes half plus, becomes 0.6 when there's some small quantum thing? Okay. There's a bit of definition that goes in here, because you can always rescale what you mean by SO2. But what we're interested in is the charge that appears on the right-hand side of the supersymmetry algebra. That goes without definition. So could it be that this charge gets renormalized? Okay? The charge for SO3 and higher, this is impossible. Just because charges for a non-abelian group are discrete, forced to be integers or half integers. So you cannot continuously renormalize an integer or a half integer. So at least in appropriate situations, the Z cannot be renormalized. At least when it's some charge under some non-abelian group cannot be renormalized. Now you can ask, can mass be renormalized? Well, mass in a typical field theory can be renormalized. Usually is. But if it happens here, it will take the particle which was BPS and make it non-BPS. Now, the problem with that is this. The number of states in a non-BPS representation is different from the number of states in a BPS representation. So, and we will make this argument carefully in contexts where it is correct. But roughly speaking, unless there is another field whose degrees of freedom this particle can eat up so as to increase its number of degrees of freedom, unless that happens, its mass cannot be renormalized. Let me say, I know this is an unsatisfactory argument and we'll make it more precisely where it's correct. Okay? But let's, just to give you a sense of the argument again. remember the Higgs mechanism. Remember the Higgs mechanism, let's say in the standard model. Right? You have these W bosons and these Z bosons that had 2 degrees of freedom, 2 polarizations when they were massless. But then they eat up the Higgs to become massive and get 3 polarizations. A degree of freedom counting is not violated because that 1 extra degree of freedom that goes into the polarization is the degree of freedom that would otherwise have been in the angle of the Higgs. The Goldstone mode. Okay? So typically this is how it works, right? You can't jump in degrees of freedom unless you compensate it somehow. So maybe your theory has a particle whose state content is such that combined with the BPS particle, it can give you the state content of the non-BPS particle. Maybe that is true. In which case this particle can combine with that other particle. It's very much like the Higgs mechanism, combining with the Goldstone boson, and become massive. Okay? Maybe, but it will sometimes turn out that we're in a theory where there is no suitable field available for this combining to happen. In such a theory, these BPS particles cannot be renormalized. Their masses cannot be renormalized unless something drastic, there's a phase transition or something like that in it. Okay? Just representation theory does not allow you to renormalize the mass of this particle without suddenly changing the number of degrees of freedom you're dealing with. Again, as I said, we will make this argument more precise where it is correct. This argument is a bit loose and sometimes is wrong. Okay? And we will see this as we go on. But at least this is the rough flavor of the argument. Now, this tells you that BPS particles are very robust. Because if you're in a favorable situation, so that BPS particles can't renormalize away in mass, then even when you turn on coupling constant effects, the mass of this particle cannot change. Okay? So let me give you an example. A zero brane in type 2A theory is a BPS particle. It's a massive particle, but it's BPS. But because it's BPS, its mass is predicted by the BPS formula without having to do any calculations. So we know that this mass, the theory has the same mass at weak coupling and strong coupling. And in fact, at very strong coupling, it matches the mass of a Kaluza-Klein graviton on the M theory circle. And this is the thing that allowed us to guess the type 2A theory was M theory on a circle. The fact that we knew the mass of a zero brane and weak coupling, and the fact that we knew it could change, told us we knew what it was at strong coupling, and then that helped us to understand what the theory actually was at strong coupling. Okay? That BPS, the BPS nature of W bosons and solitons in n equals 4 Yang moles was the first serious bit of evidence, and plus the fact that they matched under duality, was the first serious bit of evidence for S duality in n equals 4 Yang moles. So BPS states are extremely important states in a supersymmetric field. They're the states that are annihilated by some supercharges, and aspects of their dynamics is protected by supersymmetry. In particular, the mass cannot change, sometimes more aspects of their dynamics. And a lot of our control over the dynamics of supersymmetric theories happens through our control over BPS states. Okay? So these BPS states which we have first encountered in the simple representation theory kind of setup are very, very important. Okay, I think we can stop today's lecture here and stop our general discussion of supersymmetric representation theory. In the next 2 or 3 classes, we will discuss superconformal algebras, and then we will turn to the study of the dynamics of various theories once again. Any questions or comments before we? Okay, I sort of strongly advise you guys to look at this paper, at least to keep this paper on you, or to know about the paper, the strategy. It's very useful for looking up when you're studying a particular theory. Okay.